Hi everyone, this is the last example of chapter 9.1. It is question 191. Let's read the question first. Question 191. The sun's surface temperature is 5,778 Kelvin and its radius is 696,340 kilometer. Assuming the sun is a black body, calculate the intensity of the light received on the earth from the sun. The distance between the earth and the sun is 150 million kilometers. Now, let's write down the relevant piece of information. We are given the temperature of the sun. We are given the radius of the sun itself. So I denote it as R subscript sun. And we are given the distance between the earth and the sun. I denote it as RES for the radius between the earth and the sun. Now, before I go into the solution, I want to explain the technique I'm going to use in order to solve that problem. And the technique we're going to use is identical to what we've been using last semester in the Gauss law chapter. What we're going to do is we are going to create a sphere around the sun, and then we're going to create a second sphere with its center at the center of the sun and its outer edge, so the surface of that second sphere, barely touching the surface of the earth. Now, the way energy is emitted from the sun is in the form of electromagnetic radiation, in other words, light. And the way energy is transferred using light is each particle of light, called photon, carry a set of energy. Now, if you imagine you have a certain amount of photon being emitted, and these photons are traveling outward at the speed of light. If we were to count the number of photons of the smaller sphere and the bigger sphere, and let's say we were to freeze both frames in time, we will count exactly the same amount of photon. In other words, we will count exactly the same amount of energy. Now, if you were to let time go, these amount of photon will be exactly the same, so they will roughly have the same power output at all time. What this means is, if we were to calculate the complete power output on the surface of our sphere that has the radius of the sun, we'll find exactly the same power as our bigger sphere that starts at the center of the sun and where the surface touches the earth. All right. Now, I'm going to denote the power around the sun as P1, the power on our sphere that touches the earth, P2. Both of these has to be equal. For the power around the sun, we are going to use Stephan's law. And basically, well, first, power is intensity multiplied by area, so we use that definition. And then we use Stephan's law to replace the intensity of the sun with the Stefan-Boltzmann constant multiplied by the temperature to the power 4. Now we need the surface area of both of our sphere. The surface area is 4 pi r squared. So in this case, we got 4 pi multiplied by r squared. It's for our first sphere, it's the radius of the sun. And for second sphere, the radius is the distance between the sun and the earth. And we got our I2 over here, which is the value we're looking at and we want to find. At this point, we got all the value we need. We only need to isolate I2. Once we do, and we calculate everything, we end up with a value of 1362 watt per meter square. The true value is 1320 watt per meter square, so it's a really close approximation. All right, so keep in mind, when we're solving these type of problem, using a logic like we use while solving problem in the Gauss law chapter, we can create two spheres and the power on the surface of both spheres has to be equal. All right, so that's it with the example from chapter 9.1. Then in the next video, we are going to be introducing the chapter 9.2, the photoelectric effect, and basically it's the discovery that won Albert Einstein the Nobel Prize. So see you in the next video.